Howdy, folks. This is Keith Wiggins with PAG Waste Management. We're going to review an old document back from the 80s, Handbook of Biomass Downdraft Gasifier Engine Systems. And we're just going to go through it chapter by chapter and read out the important parts, learn some historical, interesting type of information regarding downdraft gasifiers, and basically a review of the literature from that time. Which is interesting. I was born in '78. This came out in '88, so I was already 10 by the time this came out. But that is quite a while ago. So let's get to reading. Chapter 1: Introduction and Guides to Literature and Research. Role of gasification and biomass conversion. This handbook explains how biomass can be converted to a gas in a downdraft gasifier and gives details for designing, testing, and operating and manufacturing gasifiers and gasifier systems, primarily for shaft power generation up to about 200 kilowatts. It is intended to help convert gasification from a practical art into a field of engineering and design. Although the handbook focuses on downdraft gasification as the only method suitable for small-scale power systems, it also gives extensive detail on biomass fuels, gas testing, and cleanup instrumentation, and safety considerations that will be of use to all those who work with gasifiers at whatever scale. The combustion of biomass in wood stoves and industrial boilers has increased dramatically in some areas, and forest, agricultural, and paper wastes are being used extensively for fuels by some industries. However, more extensive biomass use still waits for the application of improved conversion methods such as gasification that match biomass energy to processes currently requiring liquid and gaseous fuels. Examples of such processes include glass, lime, and brick manufacture, power generation, and transportation. Biomass, like coal, is a solid fuel and thus is inherently less convenient to use than the gaseous or liquid fuels to which we have become accustomed. An overview of various processes now in use or under evaluation for converting biomass to more conventional energy forms such as gas or liquid fuels is shown in Figure 1.1. We'll review it a little bit later. The figure shows how sunlight is converted to biomass through either traditional activities like agriculture and silviculture or new innovative techniques like energy plantations, agriculture, that are now being developed. Biomass resources fall into two categories: wet or wettable biomass like molasses, starches, and manures, and dry biomass, woody and agricultural materials and residues. Biological processes require wet biomass and operate at or near room temperature. These processes, shown on the lower left side of Figure 1.1, we'll see those later, include fermentation to produce alcohols and digestion to produce methane. Thermal processes function best using biomass feedstocks with less than 50% moisture content and are shown on the right side of the figure 1.1. The simplest thermal process is combustion, which yields only heat. Pyrolysis uses heat to break down biomass and yields charcoal, wood oils, tars, and gases. Gasification processes convert biomass into combustible gases that ideally contain all the energy originally present in the biomass. In practice, gasification can convert 60 to 90% of the energy in the biomass into energy in the gas. Gasification processes can either be direct, using air or oxygen to generate heat through exothermic reactions, or indirect, transferring heat to the reactor from the outside. The gas can be burned to produce industrial or residential heat, to run engines for mechanical or electrical power, or to make synthetic fuels. In one sense, biomass gasification is already a well-proven technology. Approximately 1 million downdraft gasifiers were used to operate cars, trucks, boats, trains, and electric generators in Europe during World War II, and the history of this experience is outlined in Chapter 2. However, the war's end saw this emergency measure abandoned as inexpensive gasoline became available. Development of biomass gasification was disrupted in 1946 as the war ended, and inexpensive 15-cent per gallon gasoline became available. That's very funny. The magnitude of damage inflicted on gasifier technology by this disruption can be seen by the fact that it is difficult for even the advanced technology of the 1980s, which is very funny too, to achieve on tests of what routine operation was done in the 1940s. The design, research, and manufacturing teams of that decade have all disbanded. We have from the past only the small fraction of knowledge that has been published, whereas the large bulk of first-hand experience in operation and design has been lost and forgotten. Gasification was rediscovered in an era of fuel shortages and higher oil prices, and there are gasifier engine projects underway in more than 20 countries. For producing process heat and electrical and mechanical power, in its rebirth, however, the existing technology has uncovered major problems in connection with effluent and gas cleanup and the fuel supply, which were less important during the emergency of World War II. Today, these problems must be solved if biomass gasification is to reemerge as a fuel source. Apparently, it is going to take a few years for the technology of the 1980s to be effectively applied to the accomplishments of the 1940s. Space-age advances in materials and control systems are available for use in today's process designs. So a continuous development effort and lively open exchange should enable us to incorporate latter-day chemical and chemical engineering techniques to build clean, convenient, and reliable systems. A recent workshop on low-energy gasification tabulates research and development needs. That was an 85 publication. The accelerated use of gasification technologies ultimately depends upon their ability to compete with fossil fuels, which in turn depends on unknown factors about resources, economics, and political conditions. At that time, in '88, gasification and other alternative energy processes were being developed slowly in the United States because of relatively plentiful supplies of low-cost gaseous and liquid fossil fuels. However, political changes could rapidly and dramatically alter the situation, talking about OPEC as well, as witnessed during the OPEC oil crisis of the 70s. The U.S. Office of Technology Assessment recently had issued a report calling for a national capability for emergency implementation of gasifiers. Now we're talking about the biomass energy potential, and here's figure 1.1 down below. Biomass energy potential. Biomass is a renewable fuel that supplies 2 to 3% of U.S. energy needs, and an even larger percentage in some other countries. OTA projects projects that biomass could supply from 7% to 20% annually from sources such as those shown in Table 1.1, which we'll show in a second. If it can be made available in a convenient form, and if conversion equipment is accessible, the potential of biomass for world use is equally great. Here's figure 1.1, the different resources that could be used: crop residues, animal manures, we know a company that's working on that right now, unused mill residues, logging residues, municipal solid wastes, that's a big one we're interested in, standing forests. Biomass is a renewable energy form with many positive features. The biomass feedstock is often a low-cost byproduct of agriculture or silviculture. It is low in ash and sulfur content and does not increase the level of carbon dioxide in the atmosphere and the subsequent greenhouse effect, provided that consumption does not exceed annual production. Care must be taken to ensure that biomass use as a fuel is on a renewable basis. Today, many countries, such as China, Korea, Brazil, South Africa, have active reforestation programs that are helping to increase the total world forest area. With continued diligence, the prospects for making biomass truly renewable will steadily improve. Section 1.3 is mostly a guide to the gasification literature. I encourage you to go through this section and check out some of the articles and books. It's pretty interesting stuff, that all the things that they had to kind of rescue from the 40s and World War II. And I feel like the authors of this paper in the 80s were a little bit more, they had a lot more hope as to how far gasification for different types of fuels would have come so far. But we're still, it seems, in the nascent stage of this technology. FEMA gasifier work. The Downdraft gasifier reached its highest development during the emergency of World War II. FEMA has taken interest in small-scale gasifiers because they could function during a period of breakdown in our oil supply due to atomic attack, which was a huge concern back then. It's actually again, another concern, unfortunately, today, or another disruption of conventional fuels. With this in mind, FEMA contracted with H. LaFontaine of the Biomass Energy Foundation to build a prototype gasifier that could be made with readily available parts and to write a craftsman manual description of gasifier construction and operation. That's in LaFontaine 87 paper. The gasifier has passed the test, and the manual is now in the process of being published by FEMA, so you probably look for that paper in FEMA. Anyway, that's Chapter 1. We'll go on to Chapter 2 next. That should be pretty interesting. The history, current developments, and future directions. Future meaning today. Thank you for listening. We'll talk with you next time.